So welcome everybody. Today I would like to talk about the Taylor case study, part B, and I want to talk about the Taylor principle, like the optimal weights, the output gap once more, and then the availability of data, and in the end, I will talk about the assignment questions. So once more, we start with this version of the Taylor rule. On the left-hand side, we have the Taylor rate. P is the inflation rate, Y is the output gap, and then we have here the inflation gap. I would like to modify this relationship in the following way, that I would like to get rid of this brackets here, so I'm multiplying through by 0.5. So we get P plus 0.5 times P. Then we have 0.5 times minus 2. And in the end, we can combine these terms. So here we have a negative 1 plus 2, which is like the one here. Then we have 1.5 times P and 0.5 times the inflation, the output gap. A big question is like, how did Taylor come up with the optimal weights for the inflation rate of 1.5 and the optimal weight for the output gap of 0.5? So why did Taylor opt for exactly this formula? So Taylor's paper is pretty silent in this respect, and hence we are going to talk about this question in detail during this lecture. In the first step, I would like to talk about the Taylor principle. And Taylor argued that the coefficient in front of the inflation rate has to be larger than 1. But what is the underlying economic argument? Let's have a look into a textbook. This is a Blanchard textbook, and let's have a look. So here Blanchard writes, in any case, Taylor pointed out that LR should be larger than 1, so the coefficient in front of the inflation gap. Why? Because what matters for spending is the real interest rate and not the nominal interest rate. So when the inflation rate increases, the central bank, if it wants to decrease spending and output, must increase the real interest rate. In other words, it must increase the nominal interest rate more than 1-for-1 with inflation. So this seems to be interesting. It's also true, but let's try to illustrate this insight by a numerical example. Let's assume first that the economy is in an equilibrium. So the inflation rate is at 2%, and therefore, like the Taylor rate is at 4%. I would like to make the following remarks. So the Taylor rate is the interest rate which is set by the central bank, or the central bank should set this interest rate. And therefore, it is the policy rate of the central bank. And in case of the Federal Reserve, it would be like the federal funds rate. So therefore, it is a nominal interest rate and not a real interest rate. So how large is the real interest rate in this setting? Real interest rate is equal to nominal interest rate minus the inflation rate. So like nominal interest rate, that's equal to 4%. Inflation rate is equal to 2%, so that the real interest rate is equal to 2%. Let's now assume that the inflation rate picks up to the level of 3%. And let's also assume here that the central bank raises the policy rate, like the Taylor rate, only on a 101 basis to the level of like 5%. So the central bank increases the Taylor rate from like 4% to 5%. How large is the real interest rate in this setting? Once more, real interest rate is nominal interest rate minus inflation. So the real interest rate is 5% minus 3% equal to 2%. So the real interest rate has not changed at all. So the central bank is not cooling down the economy by a contractionary monetary policy. The central bank has to increase its policy rate by more than the increase in the inflation rate in order to cool down the economy. Therefore, the coefficient in front of the inflation rate has to be larger than 1. So if the central bank would raise the policy rate to like 5.5%, then the real interest rate would increase. Let's have a look. 5.5% for the Taylor interest rate, the nominal interest rate, minus 3% inflation rate. So the real interest rate increases from 2% to like 2.5%, and hence the real interest rate increased, and the central bank performs a contractionary monetary policy. When the real interest rate increases, this can cool down the economy. So we have clarified by this numerical example why it is the case that the coefficient in front of the inflation rate should be larger than 1. So this is called like the Taylor principle. But what about like the other weights? So why is this equal to 1? Why is this one equal to 1.5? Why is this one equal to 0.5? So let's talk about this a little bit. So also the question with respect to the optimal weights seems to be very important. Consequently, like let's develop a more general version of the Taylor rule and say this is equal to the Taylor rate is equal to like the intercept, then the coefficient beta 1 related to the inflation rate, and then beta 2 related to the output gap. When we perform a regression analysis to estimate those weights, then like we are more or less minimizing the difference between like the Taylor interest rate and the interest rate set by the Federal Reserve. So in our case study, it is a hypothesis that maybe Taylor also performed the step and rounded the estimated coefficients to the next even digits, and maybe Taylor forgot to report this analysis to the reader. Let's assume that you are doing this kind of regression, and afterwards you have to perform like a t-test with respect to the beta 1 parameter. So like how do we have to set up this t-test? So we want to test whether the coefficient related to the inflation rate is equal to 1.5 or not. So I write down the pair of hypotheses as follows. The null hypothesis is that beta 1 is equal to 1.5, and the alternative hypothesis is that beta 1 is unequal to 1.5. How do we calculate our like t-test? The formula is as follows, like estimated coefficient minus claimed value divided by the standard error. Let's assume that with respect to the inflation rate, the estimated coefficient is equal to like hat beta 1, 1.54, and the standard error is equal to 0.18. So we plug in the estimated coefficient, which stems from our regression. We are subtracting the claimed value, which was claimed in our theoretical hypothesis, and we divide by the standard error. Then we get here like our estimated t-value, which is equal to 0.2. In our course, we always want to test on a 95% confidence level, so the following graph helps a lot. Like we have to find the estimated t-value of 0.2, which is like here. Here is our estimated t-value of 0.2. So like our conclusion is we do not reject the null hypothesis. So we do not reject the null hypothesis, and therefore the estimated coefficient equal to 1.54 is not significantly different from 1.5. It seems to be the case that Taylor also made this kind of regression and rounded the numbers to the next digit. But maybe Taylor forgot to tell us about this step in his paper. So where do we stand with respect to our outline? So we talked about the Taylor principle already. We talked about the optimal weights, and now it's time to talk about the output gap once more. So when we look at this picture, it is questionable, like why and how does Taylor receive this information that this is like a 2.2% growth trend. Like when we go like one step to the right, the curve should go down by a certain amount of billions of dollars of GDP. So I don't know like how this information of the 2.2% growth trend can be inferred like from this graph. I'm puzzled, and therefore later on you'll receive one assignment question related to this puzzle. Before we do that, I would like to talk about like one additional problem, like the availability of data. Like here, I added a new trend line in red ink. It is beginning in the beginning of 1989, which is like here. We only have information available from 1984 to 1989. So the information about how the GDP develops in 1990, 1991, 1992, this is not available at all. So like when we are in the year 1989, we cannot estimate this black trend line. Therefore, we don't know how the growth trend of GDP is. Definitely, it cannot be based on this kind of information in case that we are in the year 1989 and we want to implement like an optimal monetary policy, and we want to implement like an interest rate for the Federal Reserve. In case that we add like a trend line based on the information which is available in 1989, it would be the case that like the trend line would be much steeper, and more or less there would be no output gap in 1989. So in Taylor's calculations, however, there must be a large positive output gap in 1989 because there is a big difference between like the trend and the actual level of GDP. And therefore, like in Taylor's calculation, also the Taylor interest rate should be relatively high. So this is a question of the availability of data. Like in 1989, the information about how does GDP look like in 1990, 91, and 1992 is not available at all. So now let's come to the assignment questions. So assignment number 1 is you should use a new method to compute the output gap. So implement a new version of the output gap, compute the Taylor interest rate for each point in time, proceed as follows. Like generate a variable called observation that contains a time index that takes a value of 1 in the first quarter of 1984 and increases by 1 unit each quarter. Then you should perform the following regression, where like GDP is a natural log of the GDP level in period t. Afterwards, you should generate the GDP head variable and save this variable under the label GDP head. And in the next step, you can compute the output gap by using like the following formula. Then afterwards, like you should like generate the Taylor interest rate by once more plugging in the following information, like the intercept equal to 1, then 1.5 times the inflation rate, and 0.5 times the output gap. You should create a line graph with the Taylor interest rate and the federal funds rate over time. In the next step of the analysis, I would like to talk about the optimal weights in the Taylor rule. So I want to shed light on the question how the weights like this positive 1, the positive 1.5, and the positive 0.5 are determined. Here you should proceed as follows. You should estimate the coefficients of the following regression equation, as we have seen before, like this regression equation here, given by equation number 11. So the federal funds rate on the left-hand side, a constant, then as an explanatory variable, the inflation rate, and like the output gap. You should compare your results with Taylor's suggestion for beta is equal to 1, like beta 0 is equal to 1, beta 1 is equal to 1.5, as well as beta 2 is equal to 0.5. You should write down your hypotheses. You should perform like a two-sided test. You should conclude on the basis of a 95% confidence interval. And when it comes to the t-test, you should perform an appropriate t-test related to your hypothesis. And also here, you should conclude on a 95% confidence level. The next assignment. Like policymaker can only base their decisions on those data that are available at that point in time when the decision has to be made. Hence, the procedure of calculating the Taylor interest rate has to be adjusted. So in each point in time, only the available information can be used to estimate the trend of GDP, and afterwards you can calculate the output gap in a modified way, like you should calculate the output gap by using rolling regressions. The instructions are as follows. You should always use like 13 quarters to compute the trend of GDP. Use the data for the period Q1 1984 to Q1 1987 to compute a first trend line for GDP. Based on this regression, compute the output gap in the first quarter of 1987. Afterwards, like we drop the first quarter of 1984 and we add the second quarter of 1987. Hence, the second regression is based on the time period Q2 1984 to Q2 1987. So also here we have like only 13 data points, and this second trend line should be used to compute the output gap in Q2 1987. Like this is the end of this part of the lecture, so you know what to do in your case study and in your empirical analysis. Thank you so much. Have a nice day and bye-bye.